are given, then we'll jump into the computations. So let us start with the definition of a path and loops. So the first topic that we want to talk about is path and loops. Now before I discuss it, one thing you'll notice is that the word homotopy. So let me write this on a side margin, homotopy. So this topy can be thought of as a path, and homo means somewhat similar. So essentially what we're doing is that we are studying whether two paths are topologically equivalent or not. That's a very loose way of speaking of it, but you will get to see why we call this a homotopy a bit later on, once we define what is a path, what is a loop, and then the definition of homotopy will make more sense. Okay, so let us start. So path and loops. So let's say X is a topological space, and let I be a closed interval 0 to 1, then a continuous map let's call that map alpha maps the values of the interval to the topological space X is called a path with an initial point x0 and an endpoint x1 if alpha of 0 is equals to x0 and alpha of 1, sorry, the one should be inside the braces, is equals to x1. So how does this definition look like? Well, this is my interval, let's say 0 to 1, or maybe I should draw this in a vertical manner so that it's easier to do. And let's say this is my topological space X. I have some point x0, x1, and all the points on this path gets mapped to this topological space in such a manner that this map alpha, when it's taking the value to be 0, it's giving me x0, that means 0 gets mapped to this x0 point or x0, and when alpha takes the value of 1 from here, it gets mapped to x1, and this is the path. Again, this is a continuous map, so maybe I should use another color for that. So let's use this yellow color. So this is a path, and the definition of loop follows from the definition of path very straightforwardly, because if you know what a loop is, it's just a path, but the endpoints, let's say this is a path, okay, and if you glue these endpoints, then it becomes a loop. So if I were to make a loop, then what I would have to do is that I just have to slightly modify this definition over here. That is, all the things over here will be the same. The only modification that the definition of loop will need is that this alpha 0, alpha 1 is equals to x0. That means you are starting from x0. Let us use the red color to denote a loop, and you're coming back to x0 as well. So 0 maps to this point and 1 maps to this point as well, and this is what a loop is. Okay, now these are the very basic definitions of path and loops on a topological space. Now we define something called a constant path. a constant path in X is a map, let's denote it with Cx, that takes the data from the interval and maps it to X, and it's defined by Cx of S is equals to X for all S belongs to I. Okay, so you can think of this constant path as just a point, and even this constant path is also called a constant loop, because think of it like this. This is your topological space and this is just a point, right? So from your interval, all the points are getting mapped. Any point you take, it really doesn't matter. All the points you take from your interval, it gets mapped into this point only. And similarly, this condition over here is also the condition for a loop as well. It also satisfies the condition of a loop. That means, so let me write it down. This is for a path, constant path, and this is the constant loop thing. So what does the loop thing tell you? That you start from here, you should go around and come over here as well. And all these points on your path, that is when you are traversing the loop, is just a image of the some value of the interval, right? But when you are trying to define a constant loop, any value you take from the interval will eventually get mapped into the same point as well. So that's why a constant path is also called a constant loop. So if I call it constant loop, and then I can comment that a constant path is also called a constant loop. And the set of paths or loops in a topological space X can be given an algebraic structure as well. So what we say is that we want to see that whether we can give an algebraic structure, because we were saying, oh, we want to discuss some groups, right? So that's why we need to give some algebra to it, or so to say an algebraic structure. So now let's talk about how we can give an algebraic structure. Giving algebraic structure to a set of paths and loops in a topological space. We can give paths or loops, or so to say the set of paths and the set of loops, an algebraic structure as follows. So let's say I have some alpha and beta. These are maps that takes my data from the interval and maps to the topological space X, and these alpha and beta are such paths such that alpha of 1 will be equals to beta of 0, and then we define the product of alpha and beta as alpha beta. And this is a path in X defined by the following. So this alpha beta, both of them contains a parameter s in such a way that, let's say if I want to say that alpha, let's say 2s, I want to write it like this on the first half interval, so that all the conditions for a path that we introduced earlier is satisfied. So that's why I want to break the interval in half and put a 2 in front of s over here, and then beta is just 2s minus 1, and it will range from 1/2 of s to 1. And if I do that, then this is actually a continuous map, and from here we are actually giving them a product structure. So we are almost there, almost close to giving this a algebraic structure as well. But let me show you what does this really mean. So what I said about here is that, let's say this is my interval, right, from 0 to 1, and let's say this is my half, and let's say my path is something like this. So when I'm talking about alpha, this point will be just alpha of 0, right? And I go from alpha 0 to alpha 1, and this alpha 1 is the image of this point half, right? And look what I have done. I have done a product over here, and I explained this product in terms of a functions that depends on your interval. That means on the first half of the interval I use this alpha mapping, and on the second half of the interval I'm using the beta mapping, or so to say the beta function. So this is the familiar piecewise function that you see in your calculus course. So this product is interpreted as, first you start, let's say you start walking from here, and you use this alpha, let's say alpha is a car, you use that curve to go from alpha 0 to alpha 1. That is those 2 points that are getting mapped from the interval to the topological space. Let's say this is x0, this is x1, okay? And 1, let's say 1 gets mapped to x2. And then at midpoint you decide to change your car and use another car, and let's say this is the beta car, okay? So now from this point on you go to x2 using the beta car, okay? And this is just beta of 1. And at this point over here, so let me use another color, this point, this is the point where alpha 1 is equals to beta of 0, okay? So what does this product really means? Let's say this alpha beta, this means you start from alpha and then traverse the path generated by it, then you move on to the trajectory that is governed by beta. This is what the product means, and we'll see much of this later on. In fact, you can even do this kind of products for loops as well, and let me show you in a brief manner what do they look like. Let's say I have a point. In fact, this type of points will be called base points later on. So let's draw a loop like this. Let's say this is the loop alpha, and let's say I have another loop like this, beta. Here if I say what is beta times alpha means, right? It means that if you start from here and you go around the beta loop and you come back to x, right? That's what beta means. So you take the leftmost function or map, whatever you want to call them, you take the leftmost curve. That's what I would say. You take the leftmost curve and you go around it, and then you go around this alpha as well, and you realize that this type of products of path or loops also gives you another path or another loop. How? Again, focus on this guy. Alpha was a path, right? And then beta was a path, and their product is also a path. Now what you can do is that you can define the inverse of beta and the inverse of alpha in such a way that if alpha goes from this location to this location, alpha inverse one would go in the opposite way. So the alpha inverse one is just the opposite way, this way. This is the alpha inverse one. Okay? And similarly you can have a beta inverse one as well. If beta goes from this point, let's say this is a point k1 and this is a let's say this is point x prime some x prime, it goes from x prime to x2. If beta does that, then beta inverse 1 would go from x2 to x prime. And what about loops, right? How do we interpret the loops? Well, this beta times alpha will also be another loop. And if you recall what I said a few minutes ago, that first you go around beta, then you go around alpha, then this is just another equivalent loop, right? Something like this. If you consider that, let's say this is 2 meters, this is 3 meters. So once you go 2 meters, let's say you have a counter that reads 2, and then you go at 3 meters, that reads 3. So if you want to compute what is the total distance that you covered, that would give you a 5, right? Then you can choose another path, that if you start from x0 by setting your counter 0, and you can choose a path such that while you take a loop around point x0, you start from x0, you go around the loop and come back to x0. Now your counter will also say, oh, it's 5. So what you are saying is that if you have two loops and you take their product, then the resulting thing of that product will also be a loop. And similarly, like paths, we can also define inverse loop. So let's say gamma is a loop. Let's say we are saying that the counterclockwise direction is the positive direction. Then the gamma inverse one will be given by the clockwise rotation. Okay, so from all these things you can see that if I take the products, then I'm getting, if I take products of two similar products, two similar things, I get another similar thing, right? If I take products of a path, I get another path. If I take products of loop, I get another loop. I can define the inverses. Then you can obviously also show that they're associative, not for paths but for loops. For paths and loops, both of them, and at the same time you can also talk about the identity as well, and the identity is nothing but your constant loop or a constant path. So since all of these four criteria get satisfied, it can be shown that if you take a set of these paths or the loops, then they actually form a group, and these are called homotopic groups. So this was the idea behind setting an algebraic structure that I tried to show you intuitively with pictures rather than hardcore mathematics. So just before I finish off this discussion, I want to say that there's a comment. The inverse path or loop path alpha s of alpha s is denoted by alpha inverse of s alpha of 1 minus s. This means going in the opposite direction. So this was our motivation for saying that, oh, I can give some algebraic structures to my path or loops. Okay, and I want to make another important comment, that is the constant path C of x is not something that is given by alpha inverse 1, because if you recall that we were talking about sets of equivalent paths. So actually what we are talking about is something like this. If alpha is a path, then we are talking about the equivalence class of those paths. Like, let's say this is a point A and this is another point B, right? I can have, let's say this is a path 1, path 2, and I can have more family of paths in between, to let's say 3, 4, 5, 6, and you can think of it like this, that if you start with this, you can continuously deform this curve and make it 2, or you can take 2, you can continuously deform it to make it 4, and vice versa. So the paths between A and B in this configuration may be regarded as homotopic. So this is a continuous deformation, and since it's not just a single continuous deformation, because now you have lots of paths in between, so you say that this is a continuous set of continuous deformations. I mean, a continuous family of paths are there, and we are considering their continuous deformation. So that is what a homotopy is. Okay, so let us now move forward and define things more formally. So all the discussions that we had indicated that there should be a group structure for paths like this. So we want to now specify these homotopic groups and these operations, a group operation in the space of these paths, and we'll be mostly interested in loops. And to do these things, we want to classify paths and loops according to some neat, okay, let's forget the word neat, just let's write it like equivalence classes. And why we are doing this? We are doing this so that we can get a group structure out of it. Okay, so